Hello and welcome to this video on linear regression case study. In the previous video, we had seen how to develop a linear regression model in R. In this video, we will look at a case study on similar lines. Here, we will consider a multiple regression model unlike the last video. We have the following data set for a sea animal named abalone. The dependent variable or the variable that we want to predict is the age of the sea animal based on various features such as its sex, length, diameter, height, and so on. We have a total of 4,177 observations in the dataset, which we will import in R. Out of the various methods to import, we choose to select Import Dataset from the environment area here, and then press on From Excel. We then go to the destination where we have saved this file and select it. We name this file as abalone and import it. We view the table that we just imported. Now we will open a new script in R and save it before we start coding for the linear model. We will check the structure of the dataset we just imported. All the variables except sex are of numeric type. This is as expected. We can see it has 4,177 observations with 9 variables. Now, if we want to include the variable sex in our linear model, then we will have to convert it into some numeric form, as we cannot conduct a regression analysis with character variables. So we create a new column by the name gender in the abalone dataset and use the if-else condition for it. We write if-else abalone$sex is equal to male, then put it equal to 1, else 0. So basically we have indexed all the males as 1 and females with 0. Now when we check the abalone dataset, we can see a new column by the name gender that has been added to the abalone dataset. This concept is also known as the dummy variable in correlation regression. We will now remove the sex column from the abalone dataset by putting abalone equal to abalone square brackets followed by comma and then -1. Nothing before the comma means we want all the observations, and -1 means it tells R to remove the first column by the name sex. Now we will check for the summary of this dataset to get an overview of some of the statistical properties of the variables. As we execute it, we get the minimum, maximum, and quartile values for all the variables. In multiple regression model, it is very important that we decide what all explanatory variables do we need to predict the dependent variable. This is important and it is something that analysts can get good at only with experience. One way of getting to the important variables which have a significant impact on the dependent variable is to create a model with all the explanatory variables and then check for the significance of their respective coefficients. If the coefficient is significant, then we should keep that variable, otherwise we should drop it. However, we need to be careful of problems in multiple regression such as multicollinearity, heteroscedasticity, and autocorrelation. So we go ahead and create a model with all the variables to find the relationship between them and the age variable, which is the dependent one. We write m1 equal to lm, age followed by the tilde sign, and then a dot. Dot indicates that we want to include all the numeric variables in the dataset as the explanatory variables. The second argument is put as data equal to abalone. We now check the summary of the model generated. As we can see, we get the estimate for the intercept and all the coefficients along with their respective standard errors, t-values and p-values. All the coefficients except the coefficient for length are significant. This can be seen from the fact that they have immensely small p-values, or we can also infer this from the 3 stars placed by R to depict that these variables are significant enough to be included in the model to explain the variations in age of the abalone. The absolute t-values are also very large for these variables. Shucked weight and viscera weight seem to have negative relation with the age of an abalone. So now we will create another model where we will not include length as an explanatory variable. For that, we remove the length variable from our dataset first. We remove it in the same manner as we did while removing the variable sex. Now before we prepare the model, we will split the data into training data and test data as mentioned in the basics of machine learning video. There are different methods of splitting the existing dataset into two, test and training. We will see different methods in the subsequent videos. In this case study, we will use a package called CA tools to partition the data into two absolutely randomly. We first install the CA tools package in R. We type CA tools and then install it over here. We then activate this package through the library command. Create a new dataset by the name data1 and put it equal to sample.split, which is a function in the CA tools package. The first argument in this is the dataset we want to split, which is abalone 1, followed by the split ratio for the dataset, which is 2:3 in this example. This will split the data into two datasets in the proportion of 2/3. We will keep the larger dataset for training purpose and the smaller one for testing. The sample split function will add a column data1 to the abalone 1 dataset with values 1 and 0 in it, indicating which observation has gone to which dataset after splitting. Now we pull the training data out of the abalone 1 dataset by writing train equal to abalone 1 square brackets where data1 is equal to 1 and then comma, since we need all the columns for the observations where data1 is equal to 1. As we execute this command, we can see that a trained dataset is created which has 2610 observations from the abalone 1 dataset. For test dataset, we write abalone 1, data1 equal to 0 and then all the columns. As we check this dataset, we can see that there are 1567 observations in it. The sum of the observations in training data, which is 2610, and the observations in test data, which is 1567, is 4177, which is the total number of observations in the abalone 1 dataset. Now that we have split the data into training and testing, we will develop the model using the training data. We write m2 equal to lm age, which is the dependent variable, explained by all the numerical variables from the dataset train. Let us check the summary of m2 now. We can see that all the variables have 3 stars, which mean they are significant. Now we will check the forecasted or fitted values for age, which this model M2 has given us based on its estimates. As we execute this, we can see all the fitted values for age. We can see that the first value for age is 10.71696, second one is 9.44 and so on. Let us see the train data that we got from splitting the abalone 1 data. We can get the first 6 observations of the trained dataset by using the head function for analytical purpose. To get the coefficients of the model M2, we can write M2 $coefficients. This information was also present in the Summary tab. Apart from this, we also get to see the R-square of the model and the adjusted R-square as well. The F value of 447.1 is very big. Thus, it indicates that variables do explain the variations in age. R-square value of 54.61% tells us that the model explains 54.61% of the variations in the age variable. Now we will use the model developed by us in the test dataset for prediction purpose. We write y is equal to predict function followed by m2, which is the model we want to use for prediction. The next argument is the data on which we want to do the prediction. So we write test here. But please remember to remove the age variable from there, as that is the variable that we are trying to predict. So we write test comma -7. In reality, when we get data sets where we need to predict some values, we will not have that as a variable in the dataset. So removing it here makes complete sense. The moment we execute y, we get the predicted values for age based on the test data. First observation's age is predicted to be 9.04, second one is 7.49, and so on. This is how we can use the linear regression model for prediction through machine learning in R. We can check for the predicted values against the actual ones to see how accurate the model was in terms of prediction for age. This is it for now. Thank you.